All right, so now we are going to talk about a very important topic, which is stresses in beams. So once we start to basically deflect a beam, we're going to start to develop internal, basically, stresses in our beam. We're going to assume that the normal stresses are much, much larger than our shear stresses, and we're going to say that we're working with a beam when our length to height ratio is greater than 10. So we're going to also make some additional assumptions. Our beam is straight. We're working with linear, elastic, isotropic cubic materials. Our x-section is symmetric, and our beam is stable, no lateral buckling, and we'll talk about buckling when we very, very soon. So when you have a beam, you are going to have a neutral axis. The neutral axis experiences no stresses. So on the opposite side of the neutral axis, you'll have some either compressive stresses or tension stresses. So if we have positive bending here, you can see that the top face is going to be in compression, the bottom face will be in tension. And that is going to be kind of the key idea here. If we're in positive bending, again, positive curvature. We're going to assume pure bending and forget about basically non-uniform bending as well. So the way that we're going to, again, develop our expression and actually talk about or actually figure out how we're going to calculate stresses in a beam when we are when we're basically deflecting a beam, we are going to make the following kind of assumptions. Oh, it's also important to know that, again, you can have crack propagation in that tensile regime. So we're going to develop a geometric statement, a constitutive equation, and equilibrium conditions to develop this expression. So geometric statement, that beam is going to undergo some curvature. And we could define the curvature as we've done previously. So curvature is just going to be 1 over, again, r, or basically this our rho function here. So we're going to define our curvature that the beam experiences. We could also start to develop a constitutive relationship. So if we look, and we do a quick thought experiment here. If I look at some initial length dx, I can see, and then after some, basically looking at some displacement li, I can develop an expression for strain. And I see here that the strain is a function of the distance y and curvature. That should make sense. If y is equal to 0, if I'm at my neutral axis, I should have basically 0 strain. Makes sense. If my y is positive, I'm at the top face, I'll be in compression. If y is negative, I'm going to be in tension, positive strain. So this works. Take some geometry to get to this expression, but this makes intuitive sense from our, all of the work that we developed for stress and strain in this course. So you can start to talk about, stresses as a function of curvature, strains, not only in the direction of your bending, but transverse directions. You could even have anelastic curvature constants. So you could go into the world of anisotropy and curvature, but this is not very common. We're not going to deal with these problems too much in this course. So after our constitutive relationships, we could develop our equilibrium conditions. So we know the sum of the forces must be equal to 0. We should hopefully remember that term there, our moment of inertia. Some of the moments must also be equal to 0, and we can work through, essentially, again, defining those values. Moment of inertia pops up. For a rectangular cross-section, we should know that expression bh cubed over 12. You can also do the same thing for a circular cross-section. Remember that moment of inertia j, if you're in polar coordinates, pi r to the 4th over 4. And finally, with all of this work, we can reach one of our really critical expressions, which is the moment is proportional to the curvature times our Young's modulus times the moment of inertia. With this, we could plug in back into the expression we did previously and see that our stress is proportional to the moment and y. So that leads us to a very straightforward expression that kind of removes all the properties of the beam, with the exception of, your moment of inertia is built in there too. You could reach the same expression using an energy experiment as well. So when I'm calculating stresses and I'm trying to find max stresses, I'm going to look at where is my bending moment maximized. Additionally, I want to reduce my moment of inertia as well. So those are two competing factors, and again, y is going to change as well. Those are factors that you have to consider when you're designing beams. Now, obviously, there's limits, and we're going to get to this when we come to buckling, but we can change and choose geometry. Geometry has a huge impact on the stresses that develop in our beams and moment of inertia. So this is how we're going to calculate stresses in our beams. But before we calculate stresses, one of the key factors that we are going to have to develop in here and actually solve for our moment of inertia, we need to figure out beam deflection. And that is going to come soon. And by soon, I mean immediately now in this next lecture. See you next time.